Welcome to this lecture. In this lecture, I am going to talk about the matrix formulation of quantum mechanics. So, before starting the matrix formulation of quantum mechanics as suggested by Heisenberg and others like Dirac, we will first of all talk about the brief review of matrix algebra. So, first of all, let us define a matrix. So a matrix is a set of numbers or functions, and numbers may be real and complex, in a 2D square or rectangular array. I'm not going in detail regarding matrix algebra. I'm just briefly recapitulating the things which we have studied in lower classes. And there is no limitation on the number of rows and columns. So a matrix with m rows and n columns can be represented as let me write it down here. So if matrix A is represented either this way or this way, and m number of rows and the columns, so in general it is written as A11, A12 and so on, A1n and A21, A22 and so on, A2n and so on, AM1, AM2 and so on, AMN, and here it has m number of rows and the columns, mth row, and it is known as nth column. And here let me choose this element. So this is basically this element sitting in the first row and second column. This is the way that how we recognize this. Say A12, this is the first row and the second column, and this element is lying in the second row and second column, and so on. Now if m is not equal to n, or m is equal to n, then this case is known as rectangular matrix. And this is known as square matrix. Also, if a matrix has single row, then row matrix can be defined as, or we may represent it as A11, A12, A1n. So this is known as a row matrix. Similarly, if a matrix having only one column, then this can be represented as A11, A12, and so on, AN1, sorry, A21 and AN1, right? So this is known as a column matrix. Then let us talk about a matrix addition. Next is the matrix addition. So two matrices are added if both are having the same number of rows and the same number of columns. So that means matrix addition is possible if number of rows in first matrix is equal to number of rows in second matrix. Similarly, number of rows in, sorry, not number of rows, but the number of columns in first matrix must be equal to number of columns in second matrix. That is, matrix addition is possible if both matrices have same order and corresponding elements are added together. So this can be seen mathematically as if C is the addition of two matrices A and B. This is possible if their order will remain the same and the order of the resultant matrix will also remain the same. Or in other words, I can say that Cij m cross n is equal to Aij m cross n plus Bij m cross n. Then this can be written as corresponding elements are added together. So it can be written as like this, right? So let us try to understand it with the help of general example. Say C is equal to A plus B, so it can be written as A11, A12, A1n, A21, A22, A2n, then and so on, AM1, AM2, AMn. This is A matrix, and similarly B matrix means another matrix can be written as V11, V12, V1n, and V21, V22, and so on, V2n, and so on, BM1, BM2, and BMn. Then their sum is basically the sum of the corresponding elements. So it is equal to A11 plus B11, A12 plus B12, and so on, A1n plus B1n, and it is A21, B21, A21 plus B21, A22 plus B22, and so on, A2n plus B2n, and so on, AM1 plus BM1, AM2, BM2, and so on, AMN and BMN, right? So this is a way that how we can look at this matrix addition. Then I will talk about multiplication by a scalar, another operation. If we multiply some matrix with a scalar, then it gets multiplied with every element of the matrix. So mathematically it can be represented as this. So it is lambda Aij. Lambda is some scalar. It may be a cross n. So it is lambda A11, lambda A12, and lambda A1n, and lambda A21, lambda A22, and so on, lambda A2n, and so on, lambda AM1, lambda AM2, and so on, lambda AMN. So this is a way that how we will define matrix multiplication by a scalar. Then next is a very interesting topic, that is matrix multiplication, and this suggested the use of matrices in quantum mechanics. So let us talk about matrix multiplication, or it is also known as inner product. So matrix multiplication is not simple element by element operation as we did in case of addition and the multiplication by a scalar. It's a little bit different. So first of all, let us define the condition for matrix multiplication. Matrix multiplication, that number of columns in the first matrix must be equal to number of rows in the second matrix. Number of rows in second matrix. So this is the required condition for the matrix multiplication to occur. So that means let us define two matrices in such a way such that number of columns in first matrix must be equal to number of rows in second matrix. So we are choosing here B in such a manner such that number of rows in second and number of columns in first must be the same. If they are same, that means matrix multiplication is possible because the required condition is satisfied. This is the required condition, right? Now their product is defined as that C is equal to A dot P, and it can be C I K, and the resultant matrix will be of the order of this, right? So it is L cross N, and this C I K element is represented as A I J and B J K. Their summation over J kth element defined in this manner, right? So it's the summation over J. So let us try to understand it by taking an example that how things can be written. So if we are having a matrix A and B, they're taken in such a manner that it is A11, A12, A21, A22, A31, A32. It is of the order of 3 is to 2, and let us consider another B11, B12, B21, and B22, and it is of the order of 2 by 2. The number of this columns in this and number of rows in second, they are equal. So that means their matrix multiplication is possible. Now first row is multiplied with the first row is multiplied with the first column for the first element. So that means first row is multiplied with the summation over R1 and C1, and second element can be written as first row and second column, and another is first row, only two columns are there, and similarly what I can write down it as this R2, second row first column, second row second column, and here I can write down is third column, I said third row and the first column, and this is like this, right? So this is their product. It can be written in this form. So let us multiply these corresponding elements. So it can be written as A11B11 plus A12B21. This is this with this and this with this, right? Then another element will be first row second column. So it is A11 B12 plus A12 B22. Similarly, I can write down other elements A21 B11 plus A22 B21, then A21 B12 plus A22 B22, then it is A31 B11 plus A32 B21, A31 B12 plus A32 B22, right? So this is a way that how we can calculate this the product of A and B. This is summation form to define the product, right? And this is the expanded form of that how product can be evaluated. And similarly, if I try to look at B dot A, if I try to find out B dot A, now B is a matrix 2 by 2 and A is a matrix 3 by 2. So number of columns in first is not equal to. That means this is not possible. And from all these things we can arrive at conclusion that A dot B is not equal to B dot A in case of matrices, right? So we will use this idea later on. So that means we have learned that this AB is not equal to BA. That means they do not commute, which implies AB minus BA is not equal to 0, and this is like a commutator. So I can express this quantity as in this form. And this is a very important result of matrix mechanics, which is used by Heisenberg. And this also leads to the Heisenberg's uncertainty principle. Now let us define various matrices. So first of all, let us define null matrix. Null matrix. So any square matrix A, if any square matrix A, if it is operated with O in such a manner, OA is equal to O or AO is equal to O, and such that every element of A will become, when operated with this, will be 0, then this is known as null matrix, right? And every element of null matrix is 0, right? Then let us talk about diagonal matrix. So a diagonal matrix is defined as this. A matrix can be a diagonal matrix if Aij is equal to 0 or not equal to 0, if I is not equal to j, or non-zero means aii when I is equal to j. That means the diagonal elements of the matrix are non-zero and non-diagonal elements are 0, then such a matrix is known as diagonal matrix. And this can also be written as aii delta ij, if I expressed it in this form, or in simple way it can be written as this way, then this is known as a diagonal matrix. Means all the elements may be equal or different, or maybe one, what they should be non-zero. That's the condition. Then let us talk about constant or scalar matrix. Constant or scalar matrix. A matrix is said to be constant or scalar matrix if a diagonal matrix whose all the elements are equal. That means aii, if it is equal to A, or we can say that A matrix is A delta ij, then I can say that this is a scalar or constant matrix. So this is a scalar or. So it's a special case of diagonal matrix. Then let us define another matrix that is known as unit matrix. So if every element of the diagonal matrix, is unity, or we can say that every diagonal element is equal to 1, then we can say that it is a unit matrix. So that means, let us take an example, or it can be written in the form of delta function. Then such a matrix is known as a identity matrix. Here delta ij has the property that it is either 0 or 1 depending upon where I is not equal to j or I is equal to j, right? So this is all about this unit matrix. So in the next lecture I will talk about different properties and the special type of matrices which are useful in quantum mechanics. So thanks for watching this video.